Hello, you have joined an interview-style webinar, and our topic today is creating geological models using DomainMCF and machine learning from diamond drill hole data in a production environment. Our guest today is Gretchen Moore, and I will introduce her more fully in a moment. But first of all, I'd like to start with an introduction. My name is Robert Slade. I'm a mining technology leader at Maptek, and today I'm presenting at this webinar from high atop the Palmer Divide in the small township of Elizabeth, Colorado. A few things before we get started. First, today's webinar will conclude with a 15-minute question and answer session, so please feel free to write questions as you think of them in the panel of this webinar. Secondly, you will receive a link to a recording of this webinar by email in case you'd like to see it again. It will also be available on the Maptek website at a later date. By way of introduction to Maptek's machine learning application, DomainMCF, I'd like to say the following. At the heart of our webinar today is a piece of technology that arose to global prominence and unprecedented profit. In doing so, it spurred a frenzied explosion of computer science advances over the last 10 years. During this time, we saw computer technology break through the CPU barriers, harnessing the massively parallel processing of GPUs, and then disappear into the stars at the faster than light speeds of Google's Tensor Processor Unit, or TPU. The computer science technology that drove this incredible change in such a short period of time is known by the strangely appropriate name of deep learning. This phrase was coined in 2010 by one of the pioneering researchers in the field of neural networks, Professor Jeffrey Everest Hinton at the University of Toronto. He and a few peers that included the neuroscientist Terry Seinowski and the French electrical engineer Yann LeCun, together with many others, they battled through the latter decades of the 20th century and on into the 21st century, only to find themselves at the center of a deep learning revolution. This made these researchers, along with some of their grad student genii, a talent as valuable and as sought after as an elite NFL quarterback. Professor Seinowski, who now holds the Francis Crick Chair at the Salk Institute for Biological Studies and is distinguished professor at the University of California, San Diego, wrote in the preface to his 2018 book, The Deep Learning Revolution, the following lead paragraph, and I quote, "The recent progress in artificial intelligence was made by reverse engineering brains. Learning algorithms for layered neural network models are inspired by the way that neurons communicate with one another and are modified by experience. Inside the network, the complexity of the world is transformed into a kaleidoscope of internal patterns of activity that are the ingredients of intelligence. The network models I worked on in the 1980s were tiny compared to today's models, which now have millions of artificial neurons and which are dozens of layers deep. What made it possible for deep learning to make big breakthroughs on some of the most difficult problems in artificial intelligence was persistence, big data, and a lot more computer power." End quote. Neural networks had their early successes in speech and visual pattern recognition, then on to language translation, autonomous vehicles, and many other applications we encounter daily, we use often and take for granted. Today, we are going to consider how a neural net-based machine learning algorithm can apply some of this theory to the three-dimensional patterns we know as geological drilling data sets. from common and easily recognizable data arrangements, such as drill hole logging and sampling, Maptek's DomainMCF application can train a neural net from which domains can be predicted and represented in a common block model format. Using the Maptek compute framework on the AWS cloud, this simple and easy to use application can change the way an operating mine creates useful and timely models from a large and growing data set. By the way, the MCF in DomainMCF stands for the cloud compute component we term the Maptek compute framework. It is my role at Maptek to be immersed in the technologies that show promise and potential for our industry. These usually develop in partnership with our mining industry clients. With machine learning and the application developed with one such partner in 2017, I have been given the golden opportunity to bring this powerful technology to the many geologists and modelers who deal with impossibly large and growing data sets. So in summary, DomainMCF is a simple app that is capable of absorbing very large data sets, trains a neural network, predicts a domain block model, and allows geologists to observe the results in very short time. It is only a tool among many available to the geoscientist that provides a new and very fast way to create data-driven models. This machine learning application promises to allow geologists more time to look for significant features and trends that may impact safety, productivity, and profitability in their operations. In essence, more timely and practical use of their valuable investment in data collection and storage. Our distinguished guest today is Gretchen Moore. She is joining us from Red Lodge, Montana. Welcome, Gretchen. Gretchen is a senior rock mechanics engineer for the Nye mine site at the Montana operation for Sibanye Stillwater Company. She is a registered member of SME and a CPG with AIPG. Gretchen has 19 years of experience in narrow vein underground mining. Her current focus is data utilization for ground control, risk evaluations, and predictive modeling. I would also like to acknowledge you and thank our audience for joining us for this webinar today. As a group of mining industry professionals with an interest in this exciting and dynamic field of AI, and in particular, machine learning for geological modeling. Welcome. I hope you will enjoy hearing from our guest on this important and current topic. Gretchen, thank you so much for joining us today. Would you mind providing us with a brief overview of the Sibanye Stillwater mine, the currently employed mining methods, the history, and the geology?
Sure thing. Thank you, Robert. I also want to thank everyone for joining us today, as well as our operations managers for supporting the evaluation of DomainMCF and for the encouragement to present this webinar as well. The Stillwater and East Boulder mine operations are located near the towns of Nye and McLeod in south central Montana, USA. Both are underground mines targeting platinum group metals. PGM production commenced in 1986 and has largely been uninterrupted since, with punctuated incremental efforts to expand the production output throughout the years. The principal use for our products is in the production of catalytic converters. The two principal mining methods that you can see in this next slide are mechanized ramp and fill, both overhand and underhand, which is in the image on the left, and sublevel extraction by long hole open stoping with hydraulic backfilling, which is the image on the right. In the middle of this slide, you can see what a typical ore face markup looks like, and that's in both mining methods. Since the late 1800s, the Stillwater Igneous Complex has been recognized as a source of metallic resources. Starting in the late 1930s, the copper, nickel, and chromium were identified in surface outcrops, and the chromium was mined as a strategic resource. In the 1930s, the similarity of the Stillwater igneous complex to the Bushveld igneous complex was recognized, but it was not until the 1960s that exploration began. The geologists with Johns Manville International used the Bushveld igneous complex as the exploration model. Since the PGM horizon does not typically outcrop and is generally very thin, like you saw on the previous slide, that was only about 6 feet wide, Johns Manville geologists use field mapping in conjunction with diamond drilling and geophysics, along with geochemical soils and rock sampling. In 1973, Johns Manville geologists discovered a high-grade PGM horizon and named it the JM Reef. In the context of this discussion, the reef terminology comes from applying the Bushveld terminology and is synonymous with narrow vein. The 2.7 billion-year-old Archean magmatic intrusion source is thought to be a deep-seated, mantle-derived magma injected through regional transverse faults into sedimentary rocks. The JM Reef of the Stillwater Igneous Complex is a world-class PGM stratiform magmatic reef-type deposit, much like the Merensky Reef of the Bushveld complex. Both are hosted by mafic and ultramafic layered intrusives that are considered to have similar geological origins. The PGMs occur in association with a relatively thin horizon of base metal copper-nickel sulfides. Structurally, a piece of the complex has been thrust up along the Beartooth Mountains during the Laramide orogeny. In this slide, you can see the little piece of it that's zoomed in on the left, and that is what we are mining in Montana. So the dips vary across the ore body from as shallow as 45 degrees to vertical. Most of the regional faults affecting the Stillwater complex have been grouped as west-northwest trending, thrust and reverse faults, and north-northeast trending, steeply dipping transverse faults. Local and regional structures, as well as local mafic intrusive dikes, create disturbances to mining and more difficult ground conditions.
Thank you for that introduction, Gretchen. Could you describe the production definition diamond drilling programs that are underway at the Sibanye Stillwater mine and the type of data that is collected from these programs? Could you also touch on their size and scope? You know, machine learning is all about big data.
I'd be happy to. The primary access drifts are driven about 200 to 300 feet south of and parallel to the JM Reef, which strikes roughly east-west and dips north. The primary access drifts are 300 to 400 feet apart vertically, and these are driven out in front of where we have a high concentration of existing diamond drill hole information. With every 600 feet to 1,200 feet of primary drift driven, we will campaign diamond drill the reef, targeting a 50-foot space grid through the narrow deposit. You can see in the image on the right in this slide kind of what a typical drill program would look like. The purple is the reef, and then you can see the drill hole fans that were planned to intersect that. These holes are logged in their entirety for lithology, structure and alteration, mineralization, and selectively for geotechnical data within about 30 feet to the north and south of the mineralized zone. This is all done in an external database with the final version exported to sets of Vulcan ISIS databases. To say we have a lot of data is an understatement. The lower right image has got the entirety of the Stillwater mine's drilling and all the drill holes that we have to date so far. It's kind of an oblique north-looking view. This year we are scheduled to drill, and the geologists will log upwards of 800,000 feet of diamond drill core at just the Nye site alone for perspective.
Could you provide some background on the types of geological models that your team is tasked with creating from the data that is collected at Sibanye Stillwater?
Yeah, I can touch on that. The development geologists do cross-section interpretations. This is an example of that. On the left is typically how they do them. It's polylines. It's pretty much a 2D cross-sectional interpretation. I figured I'd throw in a little sneak preview of what we're getting out of the DomainMCF modeling, and that is the image on the right. The reserve and resource geologists are responsible for updating a mineralized zone minimum mining width model that is used to design our stoping areas and calculate the reserves. Our geotechnical model is built using composited geotechnical or lithologic data to predict the anticipated ground types and the ground support required in all development and production headings. The image on the left is how we have historically done it when we use just the geotechnical data. And the image on the right is kind of the direction we started going in 2019, where we were combining both the lithologic data and the geotechnical data together. Historically, these models were only built in the areas we plan to mine, and it was fairly labor intensive to build, utilizing the ore triangulation that the geologists build for reserve modeling. It also was only done to estimate the geotechnical variables into the geotechnical block model. So there was a limitation. A complication to this methodology has been that in some cases, the geotechnical data had not been collected, where an abundance of holes that went through the reef did not run above what we would have considered the cutoff grade at metals prices at that time. So this left huge gaps in the ground type model. And when we had these gaps, the lithologic data was the next best thing. So the cross section, like I said, on the right is an example of the combined Q and rock type model.
So Gretchen, how did you come to consider machine learning and then hear about Maptek's new DomainMCF product?
So Robert, I will start with a little bit of history regarding this. In 2020, I was researching additional license types to expand the use of our geotech models and came across the announcement on your website regarding a new domain modeling product and an example case study. I want to share with you a slide out of that case study. This is a screenshot from the Roy Hill case study. So there is a reference there for where you can check out this case study yourself if anyone is interested in that. At this time, I was also about to do an update to some of the models with the conventional methods, which each would have taken about a day to do, and thought this new DomainMCF utility could speed up and automate the process.
Gretchen, what did you think when I told you this solution could take your model creation from weeks to minutes?
Yeah, Robert, I recognize that this is where the exponential value lies in utilizing DomainMCF. With the addition of new information continuously being able to incorporate that information quickly would allow us to take into consideration in our planning and forecasting, not spending our time on the mechanical piece of updates, but on the utilization of the information. I brought the opportunity to the attention of Jeff Hughes, our chief geologist at the time, and expressed that we needed to pursue submitting our data for a test case. He agreed and facilitated getting approval to go forward. I submitted an interest request and immediately got a call back from Robert and Desiree. I remember in talking with them how excited I got as they shared some of their experiences in modeling some of the other initial test cases and how well it handled structural complexity and folded deposits. Initially, I was just considering this as a way to speed up building our geotechnical block models. In this slide, you can see where the red and pink blocks are that indicate poor and very poor ground. The white polygon is where we will be mining and where the ore is modeled in this cross section. One of the key components that we worked through in the test phase was modeling the thin, that are the less than 1 foot to 3 foot thick, problematic rock types and structures for ground control. You can see in this slide where the blue is a fault that we pretty consistently have, and it's 1/2 foot thick. So we really needed that detail because when we intersect these poor and very poor rock types, it drives the instability of the drifts. When we reached the point that these were being modeled as expected, we were ready to present the results. And Robert put together a presentation on where we were at so far. Robert, do you recall our initial conversations and our eagerness to test this new product?
I do. I do remember it, and I remember you giving me a call and setting a appointment to meet with Jeff and the demonstrations as you're showing there. Thank you.
Yeah, when I saw an example of the DomainMCF output for our ground type modeling and lithologic modeling, I immediately thought about the time savings that could also be realized for our development geology group. So in this slide, the level of detail that we're getting in this merged lithologic and Q ground type model, it's nothing that we would have time to build mechanically. The development geologists are responsible for designing the drill programs, logging, and interpretation. I thought that the drafting work involved in the interpretation piece could really be handled well through DomainMCF application, and they could potentially spend more of their time on the interpretation and structural modeling, more so than on drafting cross sections.
Gretchen, what steps did you take in evaluating DomainMCF and the potential it had for delivering improvements to your modeling at Sibanye Stillwater?
So in late June of 2020, I started working with you on what my vision was, and we identified what all we needed in place to get started. By July 9th, we had the first model to review and discuss. Some of it looked as expected, and some of the setup needed refining. Fortunately, our domain data is in a pretty standardized format, so there was not a whole lot of data manipulation that needed to be done to get started. We have both text lithology logging and a numeric rock code associated with that text. This filters the number of rock types down to just 21. And this really made the test successful in a short amount of time. The test model took 2 hours and 50 minutes to run. As we were developing the geotech methodology, it made sense to test how DomainMCF modeled the mineralized domain as well when compared to our current explicit modeling workflow. This next slide is an example of what we got when we modeled our mineralized zone. So the blue is the DomainMCF modeled mineralized zone, a little bit of a tongue twister there. And where the polygons are at is the explicitly modeled mineralized zone that the geologists build. The mineralized DomainMCF model for the test area took less than 20 minutes to run.
Would you talk a little bit about how Sibanye Stillwater made the choice to participate in the early access period for DomainMCF that we were currently running here at Maptek?
Yes, it was pretty exciting. Our initial test was to determine if we should budget for utilization of DomainMCF for 2021. After reviewing the results and recognizing the value of modeling where the poor and very poor ground would be, our technical services group wanted to run some additional test areas of variable complexity. In order to pursue this, we needed to define a cost structure and estimate what funding we would need in place in 2020 to budget for 2021 usage. Robert, do you recall what your response was when I asked what it would cost?
Yeah, yes, I really do, Gretchen. You know, you called me up and said, I'm doing my budget, and you kind of pushed me. And at the time, we really didn't have a cost structure built for this brand new product. So using the formula that we're proposing to take to market, which is to value this product not as a perpetual license, but to value it based upon the computing time, the MCF, if you will, compute time in the cloud. And so based upon the great demonstration work that you were patient enough to lead me through with your data and the models that we produced, the timing runs, we were able to just plug in that formula, produce a spreadsheet that gave you a 2020 estimate for your initial test models, and also at the same time provide a budget for the entire mine.
Yeah, you were fantastic working through the logic. One of the key benefits of this cost structure is that you only pay for the time it takes to run the model. All of the input setup is quite quick, and once we dialed in some of the sensitivities, I could get a model set up to run in less than an hour. As we continue going forward using this, I think it'll be less than 15 minutes setup time and probably half an hour post model run estimation run times. Model sizes were initially quite large because we needed such a small block size to get the detail. The test one was about 2 gigabytes, and this was problematic as it made it a lot less user-friendly. So without losing the details, we were able to coalesce them and cut the number of blocks and the file size by 65%. So you can see it on this slide. The block size that we coalesced to was 10 by 10 by 10, and that's based on our smallest mining unit. So it was great having Robert there from the beginning to bounce ideas off of, discuss options, and evaluate the sensitivity of the setup. The partnership approach ensured success of the model runs early on and gave us a good demonstration to share with Jeff.
Yes, this experience with Sibanye Stillwater, introducing a new application for rapidly modeling complex geology from very large data sets, has proven just how efficient and effective a close partnership has on a successful outcome and value delivery. Our new pay-as-you-go licensing system for DomainMCF made it easy to experiment and prove the value at the site with Gretchen's leadership and hard work, of course. So Gretchen, what are your thoughts on the results from your geological modeling using DomainMCF so far?
I'm excited to see this work continue. The use of it by the geologists and engineers in upcoming planned mining areas and the results of the validations. Like I said earlier, the level of detail is far greater than what we could ever achieve through manual digitization efforts in any kind of a timely fashion.
Were there other applications for machine learning in geological modeling at Sibanye Stillwater?
Yeah, for the geotechnical modeling side of it, we are going to be validating the ground type models against underground evaluations, possibly incorporating those into future models to help with planning. The slide has got basically a level cut with the ground types along that planned production heading. We've got some estimation work to do on the mineralized zones. Later this year, or maybe early next year, we also may test DomainMCF for short-range planning, incorporating face channel sampling. Our short-range and mid-range production engineers may also embark on utilizing stope optimization to speed up the turnaround time from drilling to fully designed. On a separate path, I would also like to apply it to our structural data set in a few of the more complex areas.
Excellent. Hey, Gretchen, I understand that you have reconciliation and implementation goals at Sibanye Stillwater based on your experience with learning in DomainMCF. Could you please talk about what you have been doing in the first quarter and your plans for the remainder of 2021?
Sure thing. Now that we have some test areas, we are starting in on the validation piece of this phase. Ryan McKinley, one of our development geologists, is helping get these models out to the grade control geologists for feedback. So far, the feedback is being documented, and everything I've heard from this group is really promising. The enthusiasm is great. This year, we're going to continue modeling the areas that we will add drilling in and likely go back to a few of the older areas where we're still mining, but we haven't modeled them yet.
So what are your expectations from DomainMCF introducing it at Sibanye Stillwater?
I envision that the models are utilized by engineers and geologists to give the operation the information it needs to more prescriptively provide ground support requirements. This slide shows a view looking north of the ore body ground types. So utilizing this in our planning is going to be key.
So do you have any final thoughts or advice for those in our audience today who might be considering incorporating machine learning in their exploration, geological modeling, and mine planning?
Yeah, one of the hurdles that we've always had is taking into consideration all of the data that we have in the optimization of underground excavation designs. This speeds up the process and reduces some of the influences of biases in interpretations. There were two key components that have come out of our work so far. The first is that the denser the data, the better the resulting model. The second is that it's really important to have concise, meaningful domain classifications going into using DomainMCF. I think I would say if you're at all considering incorporating DomainMCF into your modeling workflow, it's invaluable to take the time to structure your data inputs to achieve the goal of the final output.
So in conclusion, again, my name is Robert Slade from Maptek. I would like to thank Gretchen Moore for taking the time to join us today. Thank you so much for sharing your vision, the innovative initiatives you have begun at Sibanye Stillwater, and for the advice shared from this experience. I would also like to thank our audience for joining us today and for your interest in this topic, which we have been discussing with Gretchen during this webinar. To all our guests, we at Maptek are excited to be involved in this exciting new age of machine learning and the possibilities it holds for practicing geologists and computer modelers. For this point in the webinar, we welcome any questions or comments. Please write your questions in the question panel to start off the Q&A. Our first question is from Steve Sullivan, and it's for Gretchen. What length were the composite intervals to model the half-foot thick fault, blue on the section, and the corresponding sublot size?
Yeah, so kind of through iterations, we tried out different composite lengths and block sizes in the model setup, and I think we settled on a half-foot block size and a 0.05 foot thick composite length. And that gave us enough data points in those thin units to actually get the continuity modeling correctly. Yep.
Our next question comes from Christine Ballard. How often do you run a model?
Thanks, Christine. We're going to be running them as we drill them. So, like I said, we're probably drilling 800,000 feet of core this year. And so I envision that we're probably doing, 4 model runs a month. This might seem like a lot, but really, like I said, the setup's short and then it's running and you can go get coffee and then you get the model back and you run estimations on it. So probably four a month. I'm a little behind because we didn't get funding in place till last week for this year.
Gretchen, this next question comes from me. In an example mining block that you've described in your presentation, how many drill holes were used and how many composites make up the training data set?
Yeah, so based on the block we did, a typical production model is about 2,000 feet along strike and 300 feet high. And we modeled about 1,000 feet north-south. So our models are oriented with the ore body, and that varies just depending on the dip, like I said, from 45 to vertical. A typical data set would have about 500 holes. So that's a subset of our total database, which has a lot of holes in it. And then, like I said in the previous question, our half-foot, 0.05 foot composite lengths end up with 3.5 million roughly composite points. So that's where we're at with that.
The next question comes from Peter Lauder. How does the model compare to the actual underground mapping?
Thanks, Peter. So that's where we're at in the test phase, is we built the models and now we're going and mining where these models are built. And the grade control geologists are starting to use them on the first floor in the stopes. And it looks like it's comparing well. So we're documenting that validation piece right now. So that's part of the test. There's more to come on that. So we're going to be testing, consider it testing through like mid-year through June before we consider it, this is how we do business.
Our next question is another question I wanted to ask you, Gretchen. I'm going to slip it in here. Can you describe how DomainMCF is run? what data it needs, how the data is prepared and formatting, etc. And how easy is it to use DomainMCF to produce the models you have shown today? Sorry, but that's a throw-in from me.
No, that's okay. It's really quite straightforward. It's really simple. Once you have your area that you want to model, you build a boundary, a triangulation, and you pick your drill holes that you want to include by that triangulation. Those go into a subset drill hole database. Those are composited, and once you have your composites, you export it to a CSV, you drag it, drop it into the framework, and push run.
Excellent. Okay, thank you for that. Our next question comes from Christine Ballard. What is the timing from drilling to modeling to mining?
Thanks, Christine. Yeah, so we just had the first design stope block completed, where it was done drilling in December, and we are starting the development to it this next month. So the design completion was mid-February, I believe. So 2 months.
Excellent, thank you. The next question comes from Patricia Frisch, and she makes a statement here that you're using a 1.5 centimeter composite and not adding mapping. Is that correct?
So we're embarking on underground digital mapping now. We don't have that information yet, like our channel samples in a database that we could use, but I kind of touched on it. As we build that data set this year, we're hoping to incorporate that maybe early next year in either some sort of periodic update to the models.
If I might just add a comment there, Gretchen, with your permission. At the point that you're creating these models, they don't have any excavation. These are pre-production models. Is that correct? I mean, correct me if I'm wrong.
Yeah, so some of, like, because these are in blocks that are defined, 2000 by some strike length, by some height, there might be some production in that block already, but really it's intended when we have new drilling to run the model, and then we'll design what we've got going forward.
I'm very excited about your underground face mapping and reconciliation and some of the validation and verification work that's going to be done in 2021 on these very new modeling techniques. Thank you.
Yeah.
The next question is from Ken Moss. Discuss the training model and how you apply it to the full model, especially the difference in data density.
So the training model and the full model comes out of the training model, and the full model is what is the coalesced model. So yeah,
I think that might be a question more for me. And
I think so. You can field that one.
Well, I'll try. Ken, thank you for your question. And if I understand the question correctly, you're asking about the training model as in the data set, and the data set is aligned as very close composites, as we've mentioned, in order to pick up the micro logging in the lithology, and as Gretchen talked about, trying to pick up that 1 to 3 foot unit in a block model. And so the training model is the up to 3.5 million composites that are used to train the neural net, and then the block model, the full model, I guess, is the result of the deep learning algorithm that predicts the domain into each block, including all of these very small subblocks that we've discussed that identify these critical and dangerous lithologies. The next question is from Ken again. Does the training data set come from production? Should I answer that as well, Gretchen?
No, I think you actually touched on it in your answer already.
Right.
And it doesn't. Our data set comes from our definition drilling at this point, just because that is what we have. That's our best data.
Great. Let's keep an eye on the time here. The next question is from Peter Lauder. How long did it take to prepare the data to be used in the calculation of the model? That's a great question, because understanding and knowing your data, particularly when you're dealing with large data sets, is a really good question. Could you talk to that, please, Gretchen?
Sure. I think Peter's left already, but I'll answer that. So our data set is actually really pretty clean. And so we didn't have a whole lot of lithologies that didn't have rock codes. We did some statistics up front to see if we had some text lithologies or missing numeric rock codes, and did a little bit of work to make sure that everything had a rock code, so we didn't have null values, because if you don't have a value, it's going to put holes in your model. That cleaning of the data was something that was probably started reviewing for the other modeling process that we were updating. So by the time we had access to DomainMCF, it was in pretty good shape. So it didn't take long to prepare it at all.
I'll vouch for the fact that it's very clean, because I was able to model it almost instantly after I spoke with Gretchen and received the data set. Thank you for that. Our next question is from Gus Fombradis. Could you comment on how DMCF could be used for reconciliation? Great question.
Sure. Hi, Gus. Thank you. So reconciliation in this presentation, we're talking about, is the model reconciling with what we're mapping underground? And so are we seeing the rock types that we expect? Are we seeing the ground types that we expect? We haven't really gone down the grade estimation path yet with DomainMCF, but that might be some future work where we are estimating grade into that mineralized modeling of DomainMCF, and then also including our channel sampling with that, and some underground 3D work that is in progress. I think that's as much as I can say.
Thank you, Gretchen. We're really coming to the end of our webinar, and I just want to thank everyone at this point for all of the great questions. We have one last question, which is a beauty.
Yeah.
You can toss this back to me if you want, Gretchen.
No, that's okay.
How does the model? This is from Nicholas Pizarro. Please excuse me if I pronounced that wrongly. How does the model respond to areas with different density of data?
Yeah, so this is a data-driven neural network-based product, I guess is the right way to put it. And I was going down the path of trying to project out in front of us what we're seeing for upcoming areas that we haven't drilled yet, and it's really data-driven. So if you don't have data in the area, it's not really gonna give you a real good answer, but it will give you a good answer regarding areas where you need to get more data to have better certainty in what the model's predicting.
And I might just say one final comment on that great question from Gus. Sorry, Nicholas, I beg your pardon. One peculiarity that I've noticed in my work over the last year with our neural net product or machine learning product is that when it encounters or it moves beyond great density of data drilling, what I see, and is typical of this type of deep learning algorithm, is that it continues trends beautifully, so that you don't see a termination, but you see a continuation of what it's known. It gives a very geological extrapolation. Obviously, you're into the extrapolation zone, and you do.
Robert, I think you cut out there, but that's exactly it.
Oh, we are at the end of our webinar. Thank you, Gretchen. Thank you, everyone who's asked questions. We're sorry we haven't been able to deal with all of them, but we are at the end of time. We're extremely happy to continue discussions at a later time. Please get in contact with us, and we would be happy to talk more. It's been great fun for me and an enormous honor and pleasure to work with you, Gretchen, at Sibanye
Likewise.
Stillwater Mine. Thank you very much. And thank you, everyone, and have a great day. Be safe.